Anyway, thank you for inviting me over. And today I'm gonna tell you a little bit about old work, but it's some of the best stuff that I've done with friends, very good friends, and something that I'm continuing on with my very good friend also, Xavier Bois in France. So I tend to go very often to France nowadays. Since I work in the US, the summers you don't get paid, so you gotta find something to do and get a salary. So I am lucky that he always gives me some opportunity to work with him. And you see this here? Do you think that's a simulation or that's measurement? Yeah. So the goal is gonna be to see how to get rid of those, okay? So it's a real measurement from somewhere in Virginia. Okay, 3 parts. Half of my time, I'm gonna just cover background. And for you to really understand how to, where is all this coming from. And I'm gonna talk about monitoring using, by injecting signals into the system to improve estimation accuracy. Not precision, but accuracy. And then I'm going to talk about how we can take care of that nasty problem that you saw there, which is, I always motivate my work with some problems that I found in the field. I'm trying to switch slide, but it refuses to do it. So, is it here? Okay. All right, sorry, it took me longer because I couldn't get it to move. Anyway, so a lot of this work has been done with many people and funded by others. So Vedran was my PhD student. I think he just switched to university. And then Shor, he was a postdoc at the Supergrid Institute in France that we shared with Abdelkrim and Xavier. And then my students have helped developing some of the simulation models to do the proof of concept that we built. And of course, the Dominion Energy funded a lot of the work with the students. And I just spent years, my sabbatical in Mitsubishi Electric Labs, where I got to improve and repackage some of the simulation models that you can reuse thanks to them. So, and then I stolen some stuff from Jaime and from the Ecuadorian system to show you some other interesting real-world problems. So I'm pretty much sure that all of you are familiar with this, but in the interest of the audience out online, what do we say when we talk about power system dynamics and stability? I mean, it's a big words. I try to synthesize this with small condensed concept, right? So you have a grid, and it faces perturbations. So when you face perturbations, you have really disturbance forces, and somebody has to. You have a force, apply a action, you have to react. You maintain the balance and the equilibrium. So if you're not able to do that, you become unstable. Being able to maintain that synchronism to mitigate those disturbance forces is what you make the system keep stable. So in order to be able to do this in an interconnected system, you have so many loops. Inside of a power plant, you have several loops, but inside of the whole system, is so many things that have to function properly for this to happen. To me, it's a miracle that we don't have blackouts all the time. So when you try to study these things, you often make simulations. And simulations, actually, even though it's a numerical calculation, the result is a qualitative analysis. You look at it and you say, okay, this one's stable and this one's stable. So, but it's not quantitative. And to monitor something, you need to quantify it, okay? So how do you quantify is important. This nice little example here is for those that are doing the tutorial tomorrow. So this is what we're gonna build. And basically you have 2 versions of this model, one that becomes unstable, so it grows unbounded. That's the loss of synchronism, that the signal grows unbounded. And the other one that has very good, nice damping. the red one for those that are online. Okay, so how do you do a quantitative characterization? So since we have to adjust to all these small changes, this will require you to maintain that those disturbances versus to maintain what we call small signal stable. So as the load moves, as the power plant redispatches, as you move, this has to be maintained. And well, while you could do a simulation all the time to track what is the evolution of the system, that will be very complicated and it will not tell you how much quantitatively it is. So basically what you can do, since you're in this region that the system is operating 99.9% of the time, is boring, it's just, in that region, you could try to quantify that. Now, if you have simulation models, you go and you linearize it. So you have your nonlinear system, and then what you can do is that you can, to find the trajectory of the states, you have the initial condition and you take that integral. Well, if you define a small deviation, you take the Taylor series and you end up with this approximation where A is the state matrix. And that state matrix has an analytical solution. So you already know the trajectories just by doing that. So solving this problem boils down to solving this equation. And in this equation, we can now quantify things. And what we can quantify is each of the eigenvalues that are those dynamics that we're trying to track. And those eigenvalues will have a mode with a frequency and a damping. So that's what you can quantify, either from a simulation model or, more importantly, from real-world measurements. So to motivate how to do it with measurements, I just went to Ecuador last year. I really loved visiting there. And I visited the control center, and we were discussing these things. And the way that they have quantified this has been analyzing measurements, not with models. So they characterize the dynamics of their system, and you will have intra-plant, so interactions between generators in the same plant. You'll have local modes that basically are one power plant, like in this case, the largest power plant in Ecuador is one of the, I think it's the largest, is here. And it has a local interaction with the rest of the system. But it also observes and participates in the interconnection mode that is from Colombia all the way to Ecuador. And they have characterized all of this with measurements. And that's much, much harder than playing around with models, even though I love models. So Peter already talked a lot about PMUs and so on, so I'm not gonna spend any much time. But basically, if you're gonna do things based on, nowadays the fancy word is data-driven. You have been doing data-driven since the 1960s with system identification. So anyway, you need to get the data from somewhere, and you have the PMUs like Peter mentioned. So what I would like to emphasize is the concept of a wide area system is that you have these PMUs in many substations across a widespread geographic area, okay? And on top of that, you have to build some intelligence, something that can take the measurement data and synthesize and extract information. And in our case, there exists this oscillation monitoring software. And that's gonna do that job of characterizing and quantifying the oscillations that we see. Continuing with the example from Ecuador that I stole from Jaime, they have about 60 PMUs in the network, all through VPN, and they have this software from Slovenia, I don't know, some weird place like that. And they have a display, and it has a oscillation monitoring tool. And guess what? They have found very nice things. So this is the largest plant, as I was telling you. It's 1,500 megawatts. So that's, I mean, I haven't seen anything bigger than that in person. No, I haven't seen this in person, actually. Well, anyway, they were doing commissioning tests, and they removed the line. I don't remember which one it was exactly at this point. But look at this, how beautiful it looks. It looks like a textbook. It grows unbounded. You see? Starts growing, 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 growing. And what the oscillation monitoring tool help them try to track is this frequency right here. So at some point, the damping became negative, although that makes absolutely no sense. After zero, you can't say anything quantitatively. But the point is to be able to track when it's crossing this yellow line and goes to the red. Because you can still do something. For example, the best solution, especially with wind turbines, wind farms, is to turn them down, redispatch. So you can still do something for the period of time that you have here that could mitigate that. And that's exactly how they got rid of it. They just reduced the production, right? But they knew they were doing this to test the plant. So they were at the right moment at the right time, let's say, to mitigate this. Anyway, this was fixed. It was fixed by Jaime. And thanks to control redesign, they were finally able to dispatch the plant at full capacity after 6 years. Okay, so some people tell me, why you still work on these things? Because everything's been solved. In papers, not in the real world. The solutions written in papers are useless if they're not applied in the field. And so that's what it motivates this research I've been doing for some years. So why should we use measurement models? For those that know me well, they know that I love modeling and simulation. But there is a problem, is that they're great when you have them and when they're validated. And you could even represent a large bandwidth beyond what you can see in measurements. But the problem is that they're very hard to validate and maintain. Having a good model costs money. Just because it runs on a piece of software and you pay a license for it and that's it, that's not what the model is worth. What the model is worth is all of the engineering time that has to go in to make that model useful. So there has to be an alternative. So we can build these other type of models that can be identified for measurement data, that you don't have to wait for a disturbance to happen, but that you just use the noise, basically, to characterize the dynamics of the system. You can also do it with data. And what I am trying to, and I've given part of this talk many times, I'm trying to convince people that we need to do stage tests continuously and more commonly to be able to not only perhaps validate the models that we have, but have a better understanding of what is happening in the system. Now, data-driven models are limited by the type of measurements that we have, and that's basically Nyquist limit, right? So if you have PMUs I work with PMUs in the US, there are 30 samples per second, you can't see anything beyond 15 hertz. So if you need to monitor HVDC lines, you have to have 1 mega sample per second to see the 500 hertz oscillations. So this is a difficulty, that you have to have the right measurement data to be able to do the characterization. But for what we have, it can give us a good, useful representation, which is what? We want to extract this damping of the critical grid, the frequencies over what the spectrum allows us, right? And this we can use for monitor redesign. And what else I wanted to tell you? And what we can do now is to try to specify constraints on the accuracy and precision of the estimated damping and precision. Because you can estimate something and it could be useless. So again, what are we trying to monitor? We're trying to monitor you see this little piece at the beginning of the plot? We want to be able to track the system dynamics before they become unbounded. Okay, so we want to do that continuously. And what we can do then we want to extract information around the wiggles, around the little noise that we see. And so what we can do is that we can approximate everything with a discrete transfer function. And when you have that, you have in this the denominator, you have the poles of the system. Those don't give you damping and frequency. Those give you the poles. You have to convert them into continuous time to get S and theta. Okay? Theta is not the poles. Theta is the coefficients of the polynomial. But the solution of that polynomial will give us the eigenvalues that we need to extract the damping and frequency. And the whole point is to avoid this at the end, right? So then we can do that by redispatch or redesign. So just to give you a little bit better understanding is that we have ambient conditions. Ambient conditions is like this. The load is varying stochastically. Usually we assume that is white noise. And that is an input into the system. So the load becomes an input into the system G. And that's going to give us an output response. And that output response looks something like on the right-hand side. Then we're going to inject a signal. We're going to do an experiment, and we're going to inject a signal. And that's going to be applied to G, and it's going to give us a response. And finally, you have transients in the system that are happening due to switching, and that's going to be part of the response. So G is going to be a representation of the system of that transfer function that we have between the inputs and the outputs. But there's some known dynamics that we won't be able to capture there. So you have to have a fine line between deciding, can you put this there? Between deciding what you're going to try to capture and not. And the thing is that those responses are not separable. They're all contained within the same response, okay? So you kind of have to, this is your ambient data. I'm not going to use this, but I'm going to use this, and I'm going to try to use that in what I'll show you next. Why? Because the system operates most of the time like that, the power through a line, and then the probing response is something that we can control. So people tell me, oh, but doing experiments on the grid, that doesn't exist. And I say, yes, it does. So here's my favorite example, that is the toaster. That is the Chief Joseph Dynamic Breaker. They have experiment campaigns every few years. And what they try to do is to build these models of transfer functions, basically, that allow you to capture and characterize the dynamics of the systems from measurements. Now, this big thing is just a big resistor in shunt. So if you leave it more than 3 seconds, it will blow up. It will self-consume. So it's 1,400 megawatts, so that's as large as that power plant that was created, the oscillations. I like this example very much, and I really wish I had one of those. I put homework for my friend Rafael, he loves him. Now, we talked about this oscillation monitoring application. So those have to work with the ambient data so that you can have this idea of having some of, at least, if not alarming, because you don't want to alarm people usually, at least the ability to quantify the distance between the yellow line and the estimates that you have. And so you see the points here are basically 2 different modes that you have here, and this is the damping. So they call this a mode meter because it's measuring the damping of the system. So if you become closer to here, you go to yellow and red, basically. Okay, so you have this software, you can do these things, but can you trust it? So you're estimating something, and when you estimate things, you should ask, is the accuracy good enough, and is the precision good enough? And how can you do that? By constraining the variance. So if you take many of your estimations that they have in that picture before, right? Under normal operating conditions, you shouldn't change that much. You take many of those estimations, they should at least have a variance that is low enough. And in other words, it should look a little bit like this, right? So here's an example where we have the true damping of 0.1 and our estimate is 0.09. And you would say, well, 0.9 and 0.1 versus 0.09, that's a good estimate. The answer is no, you don't know. You don't know until you do this and you see what's the variance. So constraining the variance is very, very important, and that's going to be what we're going to use. So putting it all together, what you can do is that you can try to you can try to estimate. So this is this HVDC line that is also used to inject a probing signal. Okay? So you have the ability to inject this big transients, which you shouldn't do it really, or inject a design signal, a signal that you decide how it should look like. And from that, you can measure the AC lines and try to characterize the system and estimate the dampings and so on. Now, what you have to be careful is that not all the probing signals are equal. Let's see if this goes. Hello, senor. No, there we go. So that's a probing signal. You see, you have the system. It has a structure. Has 3 modes, I think, if I'm not wrong. Now you change the structure of the system. Boom. What's going to happen? Grows unbounded. So you have to be careful how you design the input signals. Because as the system is operating, if there is a transition, a change in the grid that you didn't notice, the same input signal could give you a different result. So that's really the best video I have to explain the importance of probing signal design. It's amazing. I love it. So what's the state of the art on that? The latest thing that I saw in the real world, there's papers, but who cares? This is done in the real world. They inject this signal. This is plus minus 20 megawatts on that HVDC line. And then, well, they have a knowledge of 30 years to do experiments in that system. Okay, so they have an understanding of the dynamics that they have there and what they want to excite a little bit. You need to excite it in order to observe it, right? So they create this signal where you have in the frequency domain, these are the frequencies that you want to inject, and it's very low amplitude, it's tiny. And then you roll them off about, I don't remember if that's 10 hertz or 1 hertz. I can't see right now, but they roll them off. So that's the state of the art in what you do in the real world. So my question is like, how do you design signals with lesser or unknown dynamics completely? Or when they are evolving, you're connecting more DRRs, your dynamics have started to change, okay? It doesn't matter what and where. The fact is that your dynamics evolve. So how do you design signals for that? The other thing is that can we reduce the control effort that is going to be applied? So if you want to use, instead of an HVDC line, a generator, you might want to reduce the amount of control effort that you're going to put in there because you don't want to degrade the field winding by making it go and do these things. You might also have a limited bandwidth. So can you reduce the control effort? Or what's most important to the few operators that have talked about this is like, they don't want this system to be impacted. They want a guarantee that nothing's going to happen if they let me inject these crazy signals. That's also why I went to Ecuador. What I'm not going to present is what you need to do before you, in the lab. I'm not going to cover that, but we are almost there to try to apply it, but I think it's going to take me another 10 years. Okay, how am I doing with time, guys? Half an hour, good, yeah, because it's usually I lose track of things. All right, so here's my one slide on system identification and experiment design. This old stuff, I love the old stuff, usually pretty good. I've never seen it. This is the framework that we're going to use. So you're going to have here an input. That's the probing signal that we design. You're going to have the system representation, G of Z. So in this picture, that's the real system, okay? G of Z is the real system. And you're going to have an output. And then for the ambient, you have an input. It's the load variations, right? And that's going to be H of C, and you're going to have an output, and your measurements are going to be Y of T, okay? In system identification, what we want to achieve here is to obtain an estimated G hat. Hat for estimation, right? Of Z of theta and H hat. So this is a model with a prescribed signal and a known parameter vector that is what we are going to estimate, okay? So at the end, this all boils down to calculating those coefficients in the numerator and the denominator of the transfer functions. That's really what it boils down to. So so that's the system identification loop. And if you design the system well enough, you can have better grid monitoring for those damping and frequency of the modes. And what you can do also is to do better damping control, because you can generate a model based on that input-output that is a reflection of what the system is looking like. Now, in experiment design, we can close this loop and repeat the experiment. And what we do is that we can add constraints on the accuracy and the precision. So that's where that idea of the imposing bounds on the variance, making the variance lower, becomes interesting. Okay, so we're gonna, well, this is the only method that I know how to use, so we're gonna use that, is the prediction error method. And in the prediction error method, remember the previous picture? That's the real system here. And at the bottom, this is our identified system, G hat and H hat. So what we're going to try to do is that we take Y, the real measure response, and Y of t, the prediction response from our models. And we're going to try to minimize the error, epsilon here, and that error is the difference between our known measurement and our estimated output. And so we're going to try to minimize this while finding the parameter vector theta. Okay? Of course, the larger the n, the more data points you have, the better precision you can achieve. But in reality, we are bounded in time. So we want to do this. I don't remember in continental Europe how often you change the set point of the plants, but in New York's real-time market, it's as often as every 5 minutes, I think, or 15. I'm not sure. So every 15 minutes, you got to change the set point anyway. So you have a bound there. So we're going to take, okay, you have to do this stuff within 5 to 20 minutes, no more than that, right? So that you have a real-world bound on that. So, and then one assumption that we're going to take when we do that is that the loads are going to be random. They're going to be independent. And the good thing, so that's not ideal, but the good thing here is that we do not make any assumption on their probability distribution, how the load behaves as in the probability space. And this, basically what I told you boils down, I like to put it here because it boils down to this little phrase. Instead of talking so much, I could just have read that, but I hope it explains. So this is really what it boils down to, is to minimize that error. So we talked about damping and frequency, and we talked about estimating these transfer function models. The problem is that when you estimate those guys, you have coefficients of transfer functions. You don't have an estimate of the damping and the frequency. You don't. You have an estimation of the coefficients of the transfer function. So normally what you have to do is add all of these steps to translate those coefficients, solve the polynomial equation, right? So you go from discrete time to continuous time, solve the polynomial equation, and once you have the polynomial equation, bang, you have the modes. So what Shor did here, and you gotta, if you really want the details, you have to read like the derivations that he did. He reformulated the set of coefficients theta A, which is the denominator. He rewrote them in terms of damping and frequency. So now when we estimate the coefficients of theta, of the new reparametrized vector, we're going to have this vector, and then we have coefficients on B and C. So what we estimate in theta A are directly estimates of the damping and the frequency. And that was probably the coolest thing, and Short really did a great job doing that. It was a lot of fun. He likes a lot doing the equation, so he's a great guy. Okay, so that was the innovation. Really, it's a paper that was 3 years old, but I really like it. I think that was, I'm probably never going to work on monitoring again, but I think that was a nice contribution that is actually useful. We're going to now add the constraint on the variance. To do that, we're going to apply a signal. So my friend Xavier Bombois is an expert. Actually, he created part of this area that is the idea of optimal experiment design. He's in Lyon in France. So if you take a signal, an input signal that is just a sum of cosines, so you have a sum of cosines, you add them together, that's your input signal. You have, and I'm taking this because this has a closed form solution. So you have AR, those are the coefficients, so how big is the amplitude? And then you have omega r, that's a fine grid that you define of frequencies in the spectrum, and theta r, that is the phase, okay? So you take the power spectrum of that signal and you have this closed form solution that is a square r, as you can tell. So in optimal design, if we want to have the optimal signal, okay, what are we going to do? It's going to depend on our objectives. And our objectives are to find a U that minimizes the control effort and the impact on the system, okay? While at the same time, given a bound on the variance, right? Minimize control effort and impact on the system under a low variance. Well, there's no free lunch. Basically, literally, there's no free lunch. So if you look here, this guy here. If you look here, what we can do is that we can choose to minimize the input of the probing signal that we're going to inject. If we minimize the signal spectrum, we're going to minimize the control effort. Or we can choose to minimize the output signal, the spectrum of Y. We can choose to minimize that. So we can put these two coefficients, and then we can put constraint on the variance nabla I. And so it's a problem of finding the trade-off between what you're going to prioritize over the other. And of course, the first step minimizes the effort, the second one, the impact on the system, so you don't unnecessarily excite it. And finally, you have C1 and C2 that are your coefficients of optimization. So what we did in our paper, because the Chur is a really clever guy, with the signal that we chose, the whole minimization problem I showed you before boils down to only finding the coefficients AR and AR square. That's the only thing that we have to find. Of course, you could also optimize the phase, but we decided just to put it random. So, I mean, you can do it, but I don't know how much you will gain from that. Okay, so in order to arrive to this, you have to solve some complicated equations that require the covariance matrix. I'm not going to cover that because it is too much. At the end, what did we achieve? If you have a dumb signal, right, that is just cosines with the same amplitude, okay? So you just add cosines, you're going to excite the entire spectrum, okay? That's this signal here. Versus exciting only where you need to. So you see here, these frequencies are lower than these ones, and these are 0, because there's no dynamics to excite that. Or you might intentionally want not to excite there. Okay, so how do we test this concept? We're assuming that we're working with real world, and in the real world, we don't have a good model, so we're gonna apply a dumb signal for a period of time that is gonna give us our base to compare with, okay? And that's gonna give us a G hat base, an H hat base, both of them in this new pre-parametrization and the covariance matrix. And then we're gonna apply the optimal procedure. Remember, there is a loop in the experiment design loop where you first go and apply a dumb, like the plain method, and then you redesign the signal and apply the optimal signal, okay? Now, remember that I said that you can specify a bound on the variance. Because we're going to, in the experiment design, we're going to apply the first part, a dumb signal. What we can use is calculate the variance that we get from that dumb signal, and then put as a constraint that our variance should be lower than what you can achieve with a dumb signal. Otherwise, what's the point of designing a signal at the end? Just inject a stupid one, just cosines, and that's it. So we have to achieve better, lower variance. Okay? And finally, once we find that signal, we apply it. Okay. So I don't have a power system yet, so I can't go. They won't let me do experiments yet, but I want to. So we have to have the ground truth. And so as another advertisement for tomorrow, you will learn how to linearize this model. And not this one, but another one. I don't call this the Kunder system because he didn't do it. It was Klein and Rogers that did it, so give them some credit. So this model is built with Modelica language and my library called OpenIPSL, my library, the library of my friends and me, which allows you to simulate without constraint on your algorithm of solution. And I need that because I have to inject noise. And I have to inject that arbitrary input signal. So that this became really handy, having done 10 years of work on that to take advantage of it here. Then, because we were working with Supergrid, they developed a library for HVDC lines. So we're going to add an HVDC line here, and then we're going to measure bus 7 and bus 9. We're going to measure the angle difference. And that was the only useful thing that I've done in my life, is to show that those signals are the ones that give you the better observability of the inter-area dynamics. And here, these guys are going to be noise with standard, white noise with standard deviation of pi 10 to the minus 4, okay? And here's the solution. So dumb signal, base procedure, and here we have C1, minimize the control effort, don't care about the impact on the system. C1 0.5, minimize control effort, but at the same time, reduce the impact on the system as much as you can. I apologize that the pictures are not at the same scale, but basically what is the lesson here? That this is a trade-off analysis that you have to do. How do you prioritize this depends a lot. Now, you can see, obviously, just from the time domain already, that we have reduced already the impact on the system. This is the output, this is the input, and this is the output. So at least from the magnitude of the signals, we're already lower, which is good. Now we have to look at it in the frequency domain, where all the secrets are revealed. So we estimate those transfer functions that we have, but I have the ground truth because I can take my linearized model from Modelica, and I can just give me my transfer function, and that's it. I have the ground truth. So you see, this is the inter-area mode, and here we have the other local mode here and the other local mode here. So what is the true system is then the blue line at the bottom, and then we have the base signal, the one that we apply the first part of the optimal procedure and the second part. And we can see that we have a very good fit. But you see, well, you don't match that. Yeah, I don't want those. Those are not the modes that I'm tracking. And the big difference is that I get away with using a fourth order model when the real system is 46. So this is what the kind of things that are interesting and fun to do with, you know, having full understanding of the ground truth versus the estimated models. Now we do 100 Monte Carlo stuff because the paper reviewers think that is useful. So here we have the mean. The true value is 1.5, so 0.15. So you see the base procedure has higher bias than or other two, optimal procedure 1 and optimal procedure 2. Then we have the variance. Well, we didn't really achieve to keep the bound lower with the choices that we made, but it's at the same order at least. What did we gain though? What we gained is the normalized signal power for the base procedure is 1, and now we have decreased the energy substantially for the two procedures. And this is what guarantees you in the frequency domain that you're not exciting the system. So you went from 100% from the base case to 60% of the amount of energy in the signal. So that's what is really cool. I'm done with that part. How much time I have left, guys? Because I'm making people fall asleep here.
About 10 minutes.
Oh, I have to rush then. Okay, let me go through quickly. So this is the story of the first picture I showed you. You have the excitation control loop with a generator. What happens is that you put a very high value on it. You create an interaction between the plant and the grid. And if you don't know about it, come on the tutorial because we're going to model that. Well, power system stabilizers were created to deal with this. But even if you have tuned them, the plant might still negatively interact. And here you have the real world case. So you have a plant dispatching about 600 megawatts. It was ramped down, and look at that. Who's there? You ramped it even lower. So this case is very interesting because usually it's counterintuitive. You would expect the dynamic to get a little crazy when you ramp it up because you're stressing the system. But the secret here is that to understand this is to understand that you might be, or remember that you might operate a generator in over excitation or under excitation mode. And this was the case. They were doing a test, and you can read this paper in Virginia. And this took us a while to figure out because there's no model. So we have to do it all from the measurements. So we found that what happens here is that you're changing set point not just of people of V2. The voltage is also changing. And as you change the set points, you might end up in a point, and this point is the, what was it? I don't remember now. It's overexcitation. So it's a leading power factor. So we ended up being a leading power factor. But the system doesn't grow unbounded. You see? It's the limiters inside of the AVR that are keeping it from growing unbounded. It's amazing, right? But at the end, what does this tell you? That even though you think we have solved everything in the world, in the real world, you have to adjust your designs. It doesn't matter if you take all the papers on robust PSS design, they don't fix this problem. Because this problem is under different operating conditions. It's not just under different contingencies, but it's different operating conditions. That's really what matters to understand there, right? Okay, here's the picture of the only PSS that I know because it's the one that I had in my lab, like Peter's. So what can I tell you about this? This evolved from being analog circuits to digital circuits. And the control structures that they have, you can't put whatever you want. I talk with the control people, they really annoy me. Oh, no, you could do the inverse model. They say, no, man, you have here lead-lag compensators, you put a gain, and you put time constant. That's all you can do. And you can't change it whenever you want to, because there needs to be some guy that goes there or connect with Modbus. So this is what you have. I mean, these computers are probably, my phone is like 20 times better than this thing. Well, not 22,000 or 2 million times better than this stuff, right? So what this boils down to is that, okay, we have limited constraint structures, but the good thing is that you look at all these little points, these are test points where you can inject signals, actually externally with a wire. So you could inject signals there. Now, when you look at design methods, when I talk to the people like Crestel Power that do all the designs in the US, they use root locus and frequency domain compensation, and they don't want to hear about anything else. Why? Because they only have an approximate representation of the grid. They don't have a good grid model. They don't even have a good plant model to start with. So normally and finally, the tools don't even give them a linearized model. They use PSSC. PSSC gives you a linearized model that depends on numerical perturbation. You have to buy another tool, or if you're like Shetil, you can buy the one from Cepel. But then you have one model that is time simulation in one tool, and the other one that is linearized that you don't know if they really match. So you're screwed. It's like no chance really using good models to do this. So what they do, design and tuning practice, is that they do a study anyway with the model as they have, and is the starting point to do the plant commissioning where they retune there on the plant. What happens is that it is not done often enough, performance of the damping will degrade over time. Oh, look at that. I had put my own alarm. So here's where system identification can help. I overextended myself, so I'm going to give you the gist of it. We're basically going to inject a signal here in front of the PSS and collect the output omega, and we're going to build an identified model. And we need to do that in closed loop because the open loop plant can be unstable. So you might have set very high gain on the AVR because you need a fast response for the transient torque compensation. But you have to do it in closed loop. So that's really the nice thing about here. And this is what I spent my summer last year doing. So we have a 3-step procedure. We will do blind or just ambient data monitoring. And we're gonna, the new thing is that we're gonna calculate a confidence interval when we identified H. H is the one that is only perturbed by the loads. Then we're gonna identify T. T is a surrogate for G of H. You can calculate G from T, okay? And based on this G, then we're gonna calculate a confidence interval for the damping that we're getting. And we, depending on what we get, we go to the third stage where we're gonna do a redesign. Before we apply the redesign, we will find if the minimum damping that we obtain here is better than, is actually what we, if the design that we have made is gonna improve performance or not. And I'm almost, well, this was all possible because I have this tool. So this is the coolest simulation I've done. So I'm not using an approximation. I have the whole grid model. I have inputs and outputs. I can linearize it. And here I can ramp it. I can add the noise, and I can inject the signal. It's a lot of fun. And then I can change the PSS parameters that I want at a given point in time when I have done the design. So this is how it looks. So look at this here. It almost looks like a real measurement. It's crazy. So I'm here is the initial operating point A. That's where we're gonna do the design. We're gonna grab this piece of data, then we apply the probing. We're gonna grab that piece of data. And then finally, after we apply the redesign there, we're gonna verify that what we did actually improved the system or not, the damping. So as I said, I'm running out of time, but in the first procedure, we only have the noise from the loads, H, the truth, because I can generate that. So you see it has these little peaks here that we don't capture. We only have an 8th order model versus 52. So that's H. Then the damping that we obtain is 5.64. That's lower than what we want. And we have a confidence interval that our damping is within this, so we can trust it. So we go next, we apply this input signal. We estimate T. We have 6.17, so we have a little bias. Our lower bound is a little bit above, but it's only 2.2% of the 5.91%. So we're close enough to trust this. And you have here the comparison of, this is a 6th order model, I think. It's a Box-Jenkins. This is the model that we're trying to redesign for. The other one is in terrarium mode. I'm not doing anything there. It's not my job. For that, I have to do other things. And finally, we apply the redesign method. Basically, the redesign method is in another journal paper, so I'm not going to go over it. I don't have time anyway, right? Okay, so we calculated the new parameters, and then we find that if we apply it, we can get 30% damping. So to do that design, this is the model that we estimate. G0 is the true system response, and G hat is the transfer function of the system itself. So based on the measurements, we can get a very good representation of the current operating condition. And we apply it, and look, it goes away. That's what we wanted to do, to remove that oscillation. But remember that I told you that as you change operating condition, you might find a problem. So what we did is to run the procedure again and not change the controller to verify that our control design is still valid. So you can do the redesign once and then monitor. Okay? And if you need to update it again, you update it again. Okay, I'm going to try to summarize this. Basically, what's interesting about I showed you is this method that we can design a signal where we can put a bound on the variance, and we can also try to minimize the energy of the control effort and the output, the impact on the system. The other thing is I could do all of this with a single model that serves as my ground truth. So I didn't have to have 10,000 tools. I just did everything with DynPOWER and with my Modelica stuff. And we could go all the way from offline to real time. We did it or in the lab. So that's pretty good. And for the redesign, system identification can really help if we try to do it by injecting signals. And I think the future work I'm going to try to, this stuff I did half of it myself, so I'm very proud of myself. As a professor, you seldom have time anymore to do anything, so I'm trying to find time to anything that you want, right? Okay, here's all the papers, and Rafael has the slides. Sorry I overextended myself.